We're going to continue what we talked about yesterday of these idea of random variables. Okay. So the biggest thing is random variables, in some respects, you can think about could be explained this way, where you have a list of every possible outcome and each of those outcomes probability. Okay, and we call this a probability distribution. And all the probabilities, if we've done them correctly, should add to 1. Because if it's every possible outcome, all the probabilities add to 1. Okay, so the first thing I want to talk about in terms of these is random variables. If they're essentially, these are always going to be a number, right? So these are a quantitative variable, but it's different than, say, a quantitative variable where I ask each and every one of you how much money you have in your pocket, or how many miles from the school do you live, or whatever. Those are all, each of you has an individual numerical value. These are possibles from a chance out process of some kind. Okay, so it's a little bit different, but procedurally they are the same. Okay, so histograms, we put the variable on the x-axis and frequency on the y-axis. Is everybody with me? Okay. Probability and frequency are the same thing. Probability is how frequently something should happen if you do a large number of trials. Okay? So, we can draw a histogram. Again, the only difference in this histogram is now we have each of our possible outcomes, and our probability is the frequency. And this histogram really would only apply if I flip these 3 coins, flip 3 coins and flip 3 coins and flip 3 coins and flip 3 coins, lots and lots and lots and lots of times. Okay? All right. Now, we were going through a lot last, we talked about the shapes, different measures of center, different measures of spread. Okay? All right. Does this histogram have a shape? And how would you describe it? Okay, so I understand why you guys would call it bell-shaped, because it kind of is. It definitely kind of is. It's a little bit too jagged for bell-shaped. Okay, we kind of need more kinds of possible outcomes for me to say normal. Okay, and we can't adjust it in such a way where I change my bin width. My bin width is going to be 1 for this by the nature of what this variable is, because they're going up by 1 each time. I can't adjust it to make it less jagged and smoother out. Okay, so instead of bell-shaped, though I don't necessarily think you're wrong, I'm still not comfortable calling it normal, because normal we typically use to describe continuous variables more so than discrete variables. Remember we talked about yesterday, discrete numbers are countable. These ones are not. These ones are countable. But I would be comfortable with saying mound-shaped. I would be comfortable with calling it symmetric. Just maybe not normal. If I asked you guys the center, you could actually give me the same thing for the mean and the median. They are in fact identical in this. What is the mean or the median of this? Where does the center appear to be? Ooh, so when we're talking about the mean and the median, we're talking about the mean and the median of our variable, which was number of heads. So that 0.375 is the frequency where the median is, kind of, okay? But it's not like, when we describe the mean and the median, we should be describing using the numbers on this axis. Does that make sense? Okay, so because our variable again is the number of heads. If you guys had to guess the mean / median, what looks to be the center of this? 1?
Yeah.
1.5.
I think it's, yeah, I would say it's right smack here, halfway in between the 1 and the 2. Okay, so the mean is 1.5. Okay, some of the measures of spread that we talked about were we talked about the range and the IQR and the standard deviation. For when I'm given just a histogram, I might say that the range is equal to 3 minus 0, which is 3. Okay. Is there, so in some respects, we kind of talked about standard deviation being like distance from the mean. Each of my possible outcomes has a distance from the mean, yeah? So, and so could we take the average of these distances? We kind of can. Okay, we can't for sure do it because we don't know how many times we've actually flipped these coins. But there's formulas that can approximate it. Okay? So, I don't need you guys to understand how to find that standard deviation. I'm going to show you how to do that in the calculator in a minute, okay? But I want us to be understanding that, so let's say I gave each of you 3 coins and had each of you flip those 3 coins 100 different times and make your histograms. Is everybody with me? That'd be really annoying. I'm not going to make you do that. That'd be super duper annoying. You guys would find it fun for about the first 15 to 20 times, and then you'd be like, I don't want to do this anymore. Okay? But what could we say about all of your histograms if we did that?
They'd be really
Accurate.
Accurate? Would they look like this one, give or take? If you each did this 100 times?
be relative to it.
They'd be close, right? And each of you would calculate your mean and they'd be about this. They wouldn't be perfect. They absolutely 100% would not be perfect. But they would be close. 100 times is a decent number of trials. Okay? Right. So, anytime we have a probability distribution, it has a mean and it has a standard deviation. Okay, it has a shape. You can arguably estimate the shape from looking at this. Okay, all right. So there are 2 things I need you guys to be able to do today. One of which is if I give you a probability distribution, find its mean and its standard deviation. It's actually going to be really, really similar to the way we did it in the past. Okay, and then by the way, we call the mean the expected value. So mean can be interchangeable with expected value. And the reason we say expected value is with probability, with probability, we don't know for sure what's going to happen. Because that's what probability is, right? It's like quantifying, it's putting a number to how uncertain we are, okay? So we call the mean the expected value because just because we don't know what's going to happen doesn't mean we don't have something we could expect to happen. Okay, so to calculate the mean / expected value and the standard deviation in the calculator, the first thing you need to do is put the values in the calculator. L1, L2. Can you guys go ahead and throw these into L1 and L2? I will also do that on my calculator. Okay, so those of you at home, if you don't have these in to your calculator, go ahead and hit pause the video until you get them in and then hit restart, because I'm going to keep rolling. We're all good, right? You guys all got it in? Okay. All right, so yes, we said that probability is frequency, how often something should occur. So before, we had a list and then we had a frequency list. That's all that's going to happen, is that your probabilities are going to be your frequency list. Okay, so we hit stat, we arrow over to calc, we still choose our one variable stats. All right, you're going to let your frequency list be your L2. I'll leave that up there for a second. So your list should be L1, your frequency list should be L2. Are we good? Okay, great. Your calculators have answers and mine does not, yes?
Yes.
Okay. That the company that makes your calculators does not make the app, make that app. So they're subtly different. Okay. So one of the things, so do you guys have a mean from your calculator? So the X bar is the mean of this distribution. That is your expected value. Okay. Your expected value is just equal to X bar. And can you guys help me out? What does your calculators throw out at you there?
2.823.
2.823. Great. And your standard deviation?
Doesn't have one.
Oh, hold on. It does give you one. It only gives you a population one. What is the population one?
1.696.
1.696. Great. Okay, you guys. Is this actual data or is this theoretical data if probabilities are being attached? It's theoretical. This isn't the result of a sample. This is describing this kind of theoretical population. So your calculators are smart enough that if these are probabilities, I should do it this way. Your calculator knows that it knows these are probabilities because they added one. Okay? And so it's smart enough to know that this is describing a population. So it's not going to give you an S because it's not describing a sample. It's only going to give you the sigma. Everybody okay? All right, now. When what we have are a mean and a standard deviation, the way we decide our events unusual, and this is going to pop up a lot in the next couple of days, anything that is more than 2 standard deviations from the mean is considered unusual. So do we have any? So what would it, in this scenario, 2 standard deviations from the mean, I would do 2.823 plus or minus 2 times that standard deviation. So can you guys do minus 2? And you guys do plus 2 for me? What did you guys get for the minus?
Negative 0.557.
6.217.
Okay, so if these are my observations, or my events, my possible outcomes, are any of them unusual? Well, we don't have any negative ones, so no, nothing low unusual. Our biggest one is smaller than this, so in this case, we don't have any unusual events. Okay. So which events are unusual? None. Now, if we have we have this table, we can find different probabilities. For example, You guys, if I asked you, what is the probability that this variable is equal to 4.1? What would you say? That's describing this row. So the probability is 0.18. What if I asked you the probability x is greater than or equal to 5.7? Which of our outcomes are greater than or equal to 5.7? That would be describing these, right? So what would we do? We could just add up those two. So if I have a list of all those probabilities, I can use that list to answer questions. Okay? So you guys do this one. What is the probability we get a value of 1.75 or less? That's like saying, was the probability x is smaller than, less than or equal to 1.75? What would you guys do?
We subtract.
Say that again.
We subtract the frequencies from 7 with 1.75 and up.
So what would it mean for x to be less than or equal to 1.75?
Top three.
That's essentially, that's describing the top 3 rows of the table.
Yeah.
Okay, so for x to be less than or equal to 1.75 in this setting, that means x could be 0, x could be 1.5, x could be 1 3/4. What's the probability it's one of those 3? So what we do is add together those probabilities. So think of, there's no difference between me saying, think of it this way. There's no difference between me saying x is less than or equal to 1.75 and the probability x is equal to 0, or x is equal to 1.5, or x is equal to 1.75. And we learned yesterday that addition rule, that or means we add probabilities but subtract overlap. Well, there's no overlap in these distributions because they're each row is a mutually exclusive event.
Okay.
So does that help to think of that
Yeah.
as an or? Okay, so then that becomes 0.10 plus 0.13 plus 0.26, and I think that's 0.49. Okay. So can you guys, I'm gonna pause recording. Those of you at home, pause and try these, and then also, I want you guys to try these ones on your own just to get a feel for, do you understand what's going on? And then when we're done with that, we're done for today. And like I said, you guys would have some time to finish up the lab / the Unit 4 homework. Okay. Now, the bottom one, you worked by doing adding everything, but like if you still got this because you added all of those numbers, absolutely okay. Not a problem whatsoever. Do we want to talk about any of these? Yeah.
Why would, for C, why would it be 2? Like,
It's always it's always 2 standard deviations when what you have when what you have is just a mean and a standard deviation.
okay.
You always just use those 2 things. It's always 2.
Okay.
So if we're using, like last unit, we also used the IQR. Like if you're using the IQR, it's 1.5 times the IQR. It's 2 times the standard deviation.
Yeah.
It's just 2 different sets of rules.
Okay.
And I wish I could tell you that statisticians found one better than the other, that you could just follow this one, but that's just not how we operate. We kind of think about things in from multiple perspectives. Okay. Can I give you guys one other real quick side problem to lay the groundwork for the hardest part of what tomorrow is going to look like? Okay. So I'm going to add in one more probability distribution on the bottom. But now I'm only going to give you this. And I want to know, what is the probability x is greater than or equal to 3? But so the possible outcomes in this setting are going to be anywhere between 0 and 4. Okay? But I'm only going to give you the probabilities for 0, 1, and 2. But I want to find bigger than or equal to 3. So I don't know these two things, correct? Everybody good? What do I know about the total of the probabilities between 0 and 4? It has to equal 1. Okay. Now, what are the probabilities for between 0 and 2? 0.4. Those add up to 0.4? So what would these ones have to be? So that total I get 1. 0.6. Are we comfortable with that reasoning? So in some respects, what I can do is I can say that the probability that x is greater than or equal to 3 is actually 1 minus everything else. And so as we can start thinking through what is that everything else? So that if I know this one, I can find this one. Is this okay? So we'll deal with that a whole lot more tomorrow in a slightly different context. But we're going to be using that reasoning tomorrow in a way that sometimes is a concept that students historically have struggled with. So I wanted to help you visualize it now. Okay? All right.